Hello students. So, today is the fourth lecture on derivatives. In the last lecture we looked at the chain rule for differentiation, and then we were looking for derivatives of inverse trigonometric functions. In the last class we calculated the derivative of sin inverse of x and tan inverse of x, and then I said that similarly we will calculate the derivative of other inverse trigonometric functions in the next class. So, we saw before that d by dx of the derivative of sin inverse of x is equal to 1 over square root of 1 minus x square, and derivative of tan inverse of x is 1 over 1 plus x square. Now, in the lecture of trigonometry you must have learned some identities. So, we know that sin inverse x plus plus cos inverse x is equal to pi by 2, and tan inverse x plus cotangent inverse x is also pi by 2, and similarly for secant inverse x plus cosecant inverse x is pi by 2. So, once I know the derivative of sin inverse x, I can calculate the derivative of cos inverse x using this identity. So, therefore, cos inverse x is nothing but pi by 2 minus sin inverse x. This implies that the derivative of cos inverse x is equal to the derivative of pi by 2 is 0 minus d by dx of sin inverse x. So, we get this is equal to minus 1 over square root of 1 minus x square, and similarly derivative of cot inverse x is equal to minus of derivative of tan inverse x, which is minus 1 over 1 plus x square. Now, we are left with the derivative of secant inverse x and cosecant inverse x. So, if I can calculate the derivative of secant inverse x, then again the derivative of cosecant inverse x will be negative of the derivative of secant inverse x. So, let us calculate the derivative d by dx of secant inverse x. So, we will do the same way that we did for sin inverse and tan inverse. Let y is equal to secant inverse x, then x is equal to secant of y. So, if I differentiate with respect to x, we get left hand side the derivative of x is 1 is equal to d by dx of secant of y, and by chain rule this is equal to d by dy of secant y times dy dx. This is by chain rule. But what is the derivative of secant y? We know this is equal to secant of y times tan y times dy dx. This implies the derivative dy by dx is equal to 1 over secant y times tan y. We want to express this derivative in terms of x, y was secant inverse of x. So, secant of y is, since secant of y is equal to x, I can replace secant y by x here. And what about tan? So, tan square of y we know is secant square y minus 1. So, this is equal to x square minus 1. This implies tan y is plus or minus square root of x square minus 1. Now, we have to determine whether this is positive or negative sign. So, recall from your trigonometry lectures that secant inverse of x, if I write, that is my secant inverse of x, this belongs to 0 to pi by 2 if x is greater than 1. So, and this is in pi by 2 to pi if x is in minus infinity to minus 1. So, this is because the secant inverse of x is always between 0 to pi and it can never be pi by 2, and if x is bigger than 1, then bigger than or equal to 1, then secant inverse x is less than pi by 2 and greater than equal to 0, and if x is less than equal to minus 1, then secant inverse x is greater than pi by 2 and less than equal to pi, and secant inverse x is not defined for secant inverse x is not defined if x is between minus 1 and 1. This is because secant of theta is always greater than equal to 1 or less than equal to minus 1. So, therefore, y is equal to secant inverse x. This we got that this is in 0 to pi by 2 if x is between 1 and infinity, and this belongs to pi by 2 to pi if x is less than equal to minus 1. Now, what we want is we want to find what is tan of y. So, we know that y is in the interval 0 to pi by 2 for x greater than equal to 1, and y is in the interval pi by 2 to pi if x is in minus infinity to minus 1. So, this implies tan of y, this is greater than equal to 0 if x belongs to 1 infinity, and this is less than or equal to 0 if x is in minus infinity to minus 1. This is because we know that tan function is positive in the first quadrant and negative in the second quadrant. So, therefore, if you see in the previous page we had tan y is plus or minus square root of x square minus 1. If we have x to be greater than equal to 1, then tan of y must be non negative. So, therefore, tan of y is equal to square root of x square minus 1 if x is greater than equal to 1, and this is minus of square root of x square minus 1 if x is less than equal to minus 1. This was tan of secant inverse of x. So, therefore, d by dx of secant inverse x is equal to 1 by secant y is equal to x. Let me write again, secant y times tan y, which is equal to 1 by x times square root of x square minus 1 if x is greater than equal to 1, and this is equal to 1 by minus x square root x square minus 1 if x is less than equal to 1, because tan of y is minus square root x square minus 1 if x is less than equal to minus 1. Sorry. So, we can combine this and see that if x is greater than equal to 1, then we have positive sign x, and for x less than equal to minus 1, minus x is again positive, minus x is equal to mod x, since mod x is equal to x if x greater than equal to 0 and minus x if x is less than 0. We can write d by dx of secant inverse x is equal to 1 over mod x times square root of x square minus 1, and of course, we know that this is defined if mod x is greater than or equal to 1. So, this is the formula for derivative of secant inverse x. You should remember that here we have 1 over mod x times square root of x square minus 1. So, if x is negative less than or equal to minus 1, then this will become, the derivative will be negative, and hence we also get derivative of cosecant inverse x. This is equal to minus of derivative of secant inverse x. So, minus 1 by mod x times square root of x square minus 1. Again, this is defined only for mod x greater than equal to 1. So, we have used chain rule and proved the derivative of all inverse trigonometric functions. Now, the next thing we will see is to find the derivative of a function y is a function of x, where we have y is defined as an implicit function in x. So, let me do the implicit differentiation. So, sometimes we have an equation relating y to x, but it is difficult to write explicitly y as a function of x. For example, suppose we are given y plus sin y is equal to x. So, here we know that y depends on x, but it is not possible to write y directly as a function of x, and we want to calculate dy dx. So, our aim is to find the derivative dy by dx. So, here we cannot write here, instead of trying to write y as a function of x, we will do implicit differentiation as follows. So, what we do is that we simply write the derivative. So, y plus sin y is equal to x. This implies that if I take the derivative d by dx of y plus sin y, this is equal to d by dx of x. Now, this gives, this is dy dx plus the derivative d dx of sin y is equal to 1. Now, by chain rule we know that the derivative of sin y with respect to x can be written as d by dy of sin y times dy dx, and here we are using chain rule. So, this implies that I can take dy dx common times 1 plus the derivative of sin y gives cosine y is equal to 1. This implies dy dx is equal to 1 over 1 plus cos y, provided cos y is not equal to minus 1. So, note that by doing implicit differentiation, we need not get the derivative dy dx as a function of x only. So, in this example the derivative dy dx is 1 over 1 plus cos y. Now, we do not know cos y in terms of x directly. So, in general the derivative dy dx will be a function of x and y, and we know that y implicitly is a function of x by this equation. So, that is about implicit differentiation. Now, the next thing that I would like to do is, so far we have considered functions which are polynomials or trigonometric functions or inverse trigonometric functions or some x to the some power, but there are also other functions which are very useful in calculus. So, like the exponential functions and logarithmic functions. So, I would like to introduce you the exponential and logarithmic function, and then see what the derivatives are. So, let us talk about exponential function. So, we will define exponential of x, this is equal to 1 plus x over 1 factorial plus x square over 2 factorial plus dot dot up to x to the n over n factorial up to infinity. So, this is what, this is nothing but this is equal to, this we also write as summation of n equal to 0 to infinity of x to the n over n factorial, and which is equal to the limit of summation x to the k over k factorial, k equal to 0 to n as n approaches infinity. So, this is called the power series, that we write a function as an infinite series, and any infinite series we can write as the limit of this finite series. Right. So, we will not go into much rigor here, but let me write as a fact that this series, the above series, converges, and converges means that to a finite real number for every real number x. So, the exponential function is, exponential of x is the limit to which this series converges. So, thus exponential x is defined for every real number x. Okay. So, further exponential x satisfies the following properties. One is what is exponential of 0. If you see, exponential of x is defined as 1 plus x over factorial 1 plus x square over factorial 2 and so on. If I put x equal to 0, only the first term is 1 and all the other terms are 0. So, it is easy to see that exponential of 0 is equal to 1. Second thing is that exponential of x is an increasing function of x, that is x 1 less than x 2 must imply that exponential of x 1 is less than exponential of x 2. So, this is because if you see here, if I take x 2 to be bigger than x 1, then of course, x 2 by factorial 1 is bigger than x 1 by factorial 1, and x 2 square by factorial 2 is bigger than x 1 square by factorial 2. So, each term in this power series is greater than the each term in the power series for exponential x 1. So, this is an increasing function. Of course, we know that this domain, I said that domain of this function is the set of all real numbers. So, this exponential x is defined for all r, and the range of exponential function this is equal to all positive real number. So, we will denote it by r plus, which is equal to 0 to infinity. So, the exponential x never takes negative value or 0 value. Exponential x is never 0 or negative. The fifth property I will write as what happens to this exponential x as x approaches positive infinity. If you see, exponential of x is 1 plus x by factorial 1 plus x square by factorial 2 and so on. So, if x approaches positive infinity, each of the terms except for the first term 1 approaching positive infinity. So, therefore, this limit must be equal to positive infinity, and the other one, which is not very obvious here, but let me write the limit of exponential of x as x approaches negative infinity, this is equal to 0. So, the seventh property is very important. This says that exponential of the sum of x and y is equal to product of the exponential x plus times exponential y. To compare with a to the m plus n is equal to a to the m times a to the n, if m and n are say natural numbers. Using 7 and 1, we get exponential of minus x is equal to 1 by exponential of x. This is because we know that 1 is exponential of 0, which I can write as exponential of x plus minus x, and by property 7 this is exponential x times exponential of minus x, and therefore, exponential minus x is 1 over exponential x. So, now you can see from this 6 also follows, because if x goes to minus infinity, six follows from 5, because as x goes to minus infinity, minus x goes to positive infinity, and this exponential of x you can write as 1 over exponential of minus x, that goes to positive infinity, and 1 over infinity that goes to 0. So, let us draw the graph of this function. So, we know that exponential x is defined for all x. For x equal to 0, this is 1. So, I have 0 comma 1, and this is a increasing function. So, as x increases from 0, this will keep on increasing, and it goes to infinity as you go to positive infinity. And if x is negative, then because this is increasing function, exponential of x should be less than exponential of 0, which is 1, and as you go to negative infinity, this goes to 0, right. So, this is the graph of the function exponential x. This is always increasing, it goes to negative infinity, it goes to 0 as x goes to negative infinity, it goes to positive infinity as x goes to positive infinity. Now, if we put x equal to 1, we get exponential of 1, this is equal to 1 over, I put x equal to 1. So, 1 over 1 factorial plus x square is again 1 over 2 factorial, and so on. This I can write as, this is also summation of 1 over k factorial, k is running from 0 to infinity. We know that this is some real number. Exponential of 1 is a real number, and we denote this by E. This is called the Euler's constant. So, E is exponential of 1, which is equal to summation of 1 over k factorial, k equal to 0 to infinity. In fact, we can show that this E is some real number which is bigger than 2 and less than 3. In fact, E is approximately equal to 2.718. So, though this is not important for us right now in calculus, but let me try to show to you why E is bigger than 2 and less than 3. So, we know that E is equal to 1 over 1 plus 1 over 1 factorial plus 1 over 2 factorial dot 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 up to infinity. This is of course bigger than 1 plus 1 over 1 factorial, which is equal to 2. So, E is bigger than 2. Why is this less than 3? Also, if I write E as 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on, we can write this as, this is less than 1 plus, this is again 1 plus 1 over 2 factorial is same as 2 plus 3 factorial is 3 times 2. So, this is less than 1 over 2 square, and then let me write one more term, 1 over 4 factorial. 4 factorial is 4 times 3 times 2, that is bigger than 2 times 2 times 2, which is 2 cube. So, 1 over 4 factorial is less than 1 over 2 cube, and so on. This is because if I write 1 over n plus 1 factorial, this is less than 1 over 2 to the n for n greater than equal to 2. This you can prove by induction or directly like I explained. Now, we see that here we are getting a geometric series 1 plus half square and so on, and this geometric series you might have seen that we can sum this infinite series. So, let me write this, recall that geometric series A plus AR plus AR square and so on up to infinity, this is equal to A over 1 minus R if the geometric ratio R is less than 1 in absolute value. So, this you would have seen in this sum of the geometric progression, that as you take the limit for infinite series, as long as the common ratio is less than 1 in absolute value, this converges and this is equal to A over 1 minus R. So, putting A equal to 1 and R equal to 2 gives 1 plus R equal to 1 by 2 So, AR is 1 by 2 plus 1 by 2 square and so on. This is equal to A is 1 by 1 minus 1 by 2, which is equal to 2. So, this series from 1 plus half plus 1/4 and 1/8, this sums to 2 and then I have 1 plus this. So, therefore, E is less than 1 plus the geometric sum was 2, which is equal to 3. I will just state as a fact that it can be proved that E is an irrational number. Also, let me write some limits. So, limit of n going to infinity of 1 plus 1 by n to the power n. If you look at the limit of this sequence 1 plus 1 by n to the power n, this gives us exactly equal to E, and we can also write the limit of x going to 0 of 1 plus x raised to power 1 by x, this is also equal to E. So, this fact I will not prove right now. Another thing that we will need is that, let us calculate this the limit of h going to 0 of exponential of h minus 1 over h. So, let me use this notation. So, notation we write exponential x as e to the power x also. Okay. So, if I look at, we know that exponential of h, this is equal to 1 plus h over 1 factorial plus h square over 2 factorial. this infinite series. So, this implies exponential h, I will write e to the h minus 1, this is equal to h plus h square by factorial 2, h cube by factorial 3, h to the n by factorial n, and so on. This implies that e to the h minus 1 over h is equal to 1 plus h by factorial 2 plus h square by factorial 3, h to the n minus 1 by factorial n, and so on for any non-zero h. And then it can be shown that the limit of e to the h minus 1 over h, this is equal to 1. Right. So, formally you can see that as h approaches 0, all these terms h square by factorial 3 and so on, all these terms approaches 0 and the first term is 1. So, it can be shown that this limit as h goes to 0, it approaches 1. So, this is one important limit that we will need, the limit of exponential h minus 1 over h is equal to 1. Now, we will try to calculate the derivative of e to the x. Note that e to the x is this exponential function. So, let us write f x equal to e to the x. Then to find f prime x, we need to see whether this limit as h goes to 0 of f of x plus h minus f of x over h. If this limit exists, then the limit is the derivative, and this is equal to limit of h going to 0 e to the x plus h minus e to the x over h. We know that exponential of x plus h is nothing but exponential x times exponential of h minus exponential x by h. So, we can take e to the x common, this is equal to e to the x times the limit of h going to 0 of e to the h minus 1 over h, and this limit we said is equal to 1. So, this is equal to e to the x. So, e to the x exponential function is a very special function whose derivative is itself. So, we got that the derivative d by dx of e to the x is e to the x itself. Now, once we know the derivative of e to the x, we can try to calculate some derivatives involving exponential function. What is d by dx of e to the power 5x? So, we know that we can use the chain rule, and if I write this as d 5x of e to the 5x times d by dx of 5x, this the derivative of exponential function will give me e to the 5x times 5. What is the derivative of e to the x square? This is equal to derivative of exponential is itself, but then I have to differentiate by chain rule x square, this is equal to 2x. So, I get 2x times e to the x square. Let us do derivative d by dx of tan inverse of e to the x. We know that the derivative of tan inverse of x is 1 over 1 plus x square, and then times the derivative of e to the x. So, this is equal to e to the x divided by 1 plus e to the 2x. Okay, so, this finishes today's lecture. In the next lecture, we will show that in the next lecture we will define the inverse of exponential function, which is called the logarithmic function, and then we will calculate the derivative of log of x, and then we will see some properties of logarithm and then calculate some more derivatives using these functions. Thank you.